I wanted to take a second here at the beginning of this second video of the additional aspects to aqueous equilibrium chapter to once again review the difference between the hydronium ion and the hydrogen ion. The deal is Arrhenius did not necessarily need to represent how the ionization of acids happen. He just simply thought of these as splitting apart, and you get the hydrogen ion and the resulting chloride ion. The reason that Bronsted and Lowry invented, I shouldn't say invented, it does exist, but the reason that they need the hydronium ion is because in all Bronsted-Lowry acid-base equations, there has to be both an acid and a base. In the case of Arrhenius here, there's just an acid there. There's no real representation of a base. But Bronsted and Lowry in their acid-base reactions must always have an acid and a base. And what we get here is the hydronium ion gives us the explanation for how both an acid and a base can exist. So here in the first bullet point here at the bottom, we have the acid HCl and we have water. Well, we've never thought of water as a base before, but if we take a look at what happens here, we can explain this. If we remember that Bronsted and Lowry said an acid simply had to donate a hydrogen ion, let's take a look at what HCl does here. It looks like in the reactants there is a hydrogen ion attached to the chloride ion, or what we call hydrochloric acid, but over here it has lost that hydrogen ion. So it has donated that hydrogen ion somewhere, and the somewhere is what Bronsted and Lowry had to account for, because the somewhere is the base. And water here is our Bronsted-Lowry base in this equation, because if we take a look at what has happened to water, it has accepted that hydrogen ion, and notice what happens now. We increase the hydrogen by 1 from 2 to 3, but also the charge is very important. So when we do these equations here in just a second, it's important to keep track that we both add a hydrogen and we also have to represent the charge difference as well. So I guess the main point here in the third bullet point overall is that these bottom two equations are chemically identical. They mean the same thing, except the Bronsted-Lowry equation features water because they need a base, and the Arrhenius definition does not necessarily need a base when there's an acid present. Okay, so again, as we mentioned in the first video, we got some new bases when Bronsted and Lowry proposed their new theory, and another one, I know I mentioned the I think the carbonate ion in the first video as well, or I think it was the ammonium ion, but now we're going to mention the carbonate ion here. We see carbonate right here, which again, Arrhenius cannot explain this as a base. It can't explain its behavior because there is no hydroxide ion. But if we notice what happens, here's our characteristic ion of acids, and again, we could easily just represent this like this right here, and it would mean the same thing. But if we take a look at what happens, we get the hydrogen ion is basically absorbed, you can think of it as, or accepted by the carbonate ion, and we've effectively removed that hydrogen ion from solution. It has accepted that hydrogen ion. So the next most important part here that we get to is the idea of a conjugate acid and a conjugate base pair. Okay, so if we define something as an acid, it has a conjugate base. If we define something as a base, it has a conjugate acid. And the best rule of thumb that I can give you for these is I want you to remember the term one hydrogen away. All right, we must always remember the term one hydrogen away. So if two substances are separated by only one hydrogen ion, then they are a conjugate acid-base pair, and I'll show you what I mean by that. Here we have a pretty strong acid in HCl. If we remove one hydrogen, here is its conjugate base, the chloride ion. If we go down here, we have sulfuric acid, and if we remove one hydrogen ion, we have its conjugate base, the hydrogen sulfate ion. Now, the reason I know to remove a hydrogen ion as opposed to add it is because I'm defining it first as an acid. So acids, by definition, donate hydrogen ions to solution, meaning they themselves lose a hydrogen ion. We end up with one less hydrogen ion, and there's its conjugate base. If we want to go in the opposite direction, let's go down here to the ammonia. It is a base, and by accepting a hydrogen ion, it becomes the ammonium ion. That's conjugate acid. So really, these can be bases or conjugate bases here on the left side. These can be acids or conjugate acids here on the right side. It just depends on where you start. If you start in the acid column, we have acids and conjugate bases. If we start on the right column, we have bases and then conjugate acids. A few things about these that are very important is the relationship of strength between the acids and their conjugate bases. So first of all, we won't talk a lot about conjugate acid-base pairs of strong acids and strong bases. I know they have them up here, but we generally will not refer to them. So our strong acids and bases, we typically do not say that they have a conjugate, just because there's no basicity for these ions right here because their acids are so strong. The same thing here. There's no acidity for these conjugate acids because their bases are so strong. But what is a very key thing to remember is if one is strong, the other is very, very weak. So what we have here is the strong acids. Well, their conjugate bases are very, very weak bases. And as you go down the list, we get weaker acids. They get into stronger bases. So when we get all the way to the bottom, the strongest of bases, their conjugate acids are very weak. If we end up with two kind of in the middle road here, we have kind of a weakly acidic acid and a weakly acidic base, or a medium acid and a medium base. Just know that if one is strong, the other is weak, and then you can imagine all the possible combinations that go through there. So once again, we see another reminder that strong acids and strong bases do not have an equilibrium. Only the weak acids and weak bases have equilibrium. And I want to take a second to explain, there is no medium. I know I said it a second ago. If you're strong, then that's how we'll describe it. But if you're not strong, you are then weak. There is no medium. This is technically, these are weak acids here. How weak they are is represented with an equilibrium constant that we'll talk about in just a second. But I wanted to take a second here to kind of go through basically some rules with determining conjugate acid-base pairs, because that's something that will be on the homework. So you want to basically take a look here in number 1 of what's going on. Here we have NH3, and I want to underline it, and I want to underline its partner. The acids and bases will always be on the left. The conjugates will always be on the right. So I'm going to either write A or B under these things here to the left. So what I notice is here are our pairs, NH3 and NH4+, and I got to think about what NH3 had to do to become NH4+. And to me, that makes sense that it has accepted a hydrogen ion. So that makes this the base, since it is accepted. Now that automatically makes this the acid. Now going over ammonia's pair, the ammonium here, that has to be its conjugate acid, therefore making this the conjugate base. So really the toughest part is getting started. Once you get started, you're well on your way. So I'm going to try this again here. Here is this. I'm going to find the substance that is one hydrogen away, and it's the acetate ion over here. I noticed that in order for acetic acid here to become the acetate ion, it has had to donate a hydrogen ion. Therefore, donating makes it an acid. This has to be the base because there is no such thing as a Ca or a Cb on the left side of the arrows. So then acetic acid's partner automatically becomes its conjugate base. Here is the conjugate acid. And then I will leave the last one here for you guys to try on your own, and we can talk about that as we begin class tomorrow. Okay, kind of switching gears a little bit, we get a term here that's pretty important in acid-base equilibria, and that is the concept of amphoterism or amphiprotic substances, which is what your book calls it. There are certain substances that are capable of being both an acid and a base, and that is simply what the term amphiprotic or amphoteric means, is it can be either acidic or basic, and we get the prefix amph here, which means both, so amphibians can live on water or the land. And the most common one here is water. Water can act as an acid by donating a hydrogen ion to solution. Okay, so water has acted as an acid there, but water can also act as a base by accepting a hydrogen ion. So water can be both an acid or a base, and there are plenty of other examples as well that can do this. We get the hydrogen sulfate ion right here. We can make it act as a base, and we can form sulfuric acid as a result. or we can make this act as an acid by donating that last hydrogen ion to water. So either way here, these are substances that can be both acidic or basic, and these will be pretty important for us later here in the chapter. All right, a few more things here on equilibrium. Here we're finally getting to the equilibrium concept of acids and bases. Weak acids. Weak acids are where we see equilibrium show up, and these are very important here, and this will be the most of our work here in this chapter. We have a new K for weak acids, and that is simply representing the dissociation of the acid, which we have here on the right. It looks like it's an Arrhenius dissociation because we don't see water show up, but even if we did have water show up, it would be a liquid, and therefore it would not be placed into the K expression. But you're always going to get the hydrogen ion, the anion of the acid on top, and then the protonated acid or the combined acid on bottom. Ka, now this is exactly the same thing as the K before, it's just the A means we're talking about an acid. So here we have a list over here, and the larger the Ka is, the stronger the acid. So here we have the strong acids, and again, we don't often think of these as equilibrium because the Ks are so large. But from here down, we see a representation. So not all weak acids are created alike. Here's our strongest weak acid, if that makes sense, because it has the largest K expression, meaning it's most likely to go to the right here. As we go down the list, we see very, very weakly acidic substances because their Ks are so small. So the larger the Ka, the stronger the weak acid we are. If we ever happen to get over 1, that's just a strong acid, and we don't consider that equilibrium anyway. We get the same deal with bases. This time I'm going to show you the Kb. Now the Kb will always have the hydroxide ion. It will have the conjugate acid of the base, and then the base goes on bottom. Again, we do not see water show up. So again, in order to be a base, substances basically steal a hydrogen ion from water, and that's how we get this hydroxide ion form. So we see the idea of amphoterism there. Water behaved as a base on the last page, and then now it's behaving as an acid by donating a hydrogen ion. Same deal. The larger, this time the Kb's ascend this way, I don't know why that is, but the larger the Kb, the stronger the weak base we are. So here are two pretty strong bases, not equilibrium for these guys here, but for everybody else, these are considered equilibrium scenarios. And again, the higher, the larger the Kb, the stronger the weak base we are. Here are the weakest of the bases up here. Okay, this slide is here just basically to tell you, do not freak out about the Ka and Kb. You're going to write them the same way, products over reactants. We're just replacing the Kc and the Kp with an A and a B, A standing for acid and B standing for base. Okay, so our last slide here basically is going to restate what I said before about just knowing that the larger the number is, the stronger that acid is. And that's essentially all this base, or all this slide here is about, is the larger the number, the stronger the acid is. We're still going to call these things weak. Okay, if I go back here, we're still going to call these things weak acids, but not all weak acids are created the same. Some are more acidic than others.